Imagine a language model trying to understand a sentence. Traditionally, it would process word by word, remembering the past. But what if it could instantly grasp the connections between all words all at once?
That sounds like a massive leap, like having perfect short-term memory, but also knowing what's coming. Is that what we're talking about today with the transformer?
Precisely. This paper, Attention is All You Need, introduced an architecture that makes this possible. It's a foundational text for nearly all modern large language models, including GPT.
So, the title suggests attention is the whole game. Does that mean it throws out previous common approaches like recurrent networks?
Exactly. The authors explicitly state they are based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. This was a radical departure from the dominant models of the time.
That's a bold claim. Recurrent neural networks, or RNNs, were the go-to for sequence data. Why get rid of something so established if it was working?
RNNs process tokens one after another, creating a bottleneck. This sequential nature makes them difficult to parallelize. Transformers, by contrast, are more parallelizable and requiring significantly less time to train. This efficiency gain was a major motivator.
So it's not just about accuracy, but about the practicalities of training massive models. Parallel processing is key for scaling. I remember from case TCM 093001 on Mixture of Experts.
It's both. This paper showed impressive gains. For instance, on English to French translation, it achieved a state-of-the-art BLUE score of 41.8, which is a measure of translation quality.
Better quality and faster training sounds like a breakthrough. But what does attention actually do? How does it replace recurrence without losing the context of a sequence? Especially when RNNs were so good at sequential information.
That's the core question we need to answer. The paper also noted that the transformer generalizes well to other tasks, hinting at its versatility. It's not just for translation.
Generalization is critical. So this isn't just a niche architecture, it's proven to be a fundamental building block for diverse applications. This really echoes our discussions in TCM 033001 and TCM 063005 about transformer generalization.
Exactly. To truly understand its power, we need to peel back the layers and see how this attention mechanism actually works. Let's head to a fantastic resource that illustrates it beautifully.
All right, how does attention become all you need to process sequences?
This blog post, The Illustrated Transformer, is a classic for a reason. It simplifies the complex ideas from the original paper, helping us build an intuition from the ground up with clear visuals and analogies.
It's always great to have a visual guide. So how does it start breaking down the transformer structure for us, moving beyond just the high-level idea?
It begins by showing the transformer as having an encoding component, a decoding component, similar to older sequence-to-sequence models. The encoder takes input, the decoder generates output.
Okay, that part feels familiar. So it's still an encoder-decoder structure, just with a new internal mechanism?
Precisely. Within each encoder, the key is the self-attention layer, a layer that helps the encoder look at other words in the input sentence as it encodes a specific word. It's about drawing connections globally within the input.
Ah, self-attention. So it's not just looking at the source sentence, but each part of the source sentence is looking at every other part of the source sentence?
Consider this sentence. The animal didn't cross the street because it was too tired. When we process it, self-attention helps associate it with animal, not street.
That's a classic ambiguity in language. A human understands the context. So the model learns to do that by weighting the importance of animal more when processing it.
Yes, this replaces the sequential memory of an RNN's hidden state. The author notes, self-attention is the method the transformer uses to bake the understanding of other relevant words into the one we're currently processing.
So instead of building context step by step, self-attention builds it for all words in parallel. That's the parallelization benefit we saw earlier, isn't it?
It is. The article explains the word in each position flows through its own path in the encoder. Each word gets its own computation stream, which drastically improves speed.
This means a GPU can process all words simultaneously. Before, an RNN had to wait for word n-1 to finish before starting word n. This is a game changer for speed.
Correct. However, the article clarifies there are dependencies between these paths in the self-attention layer. It's not fully independent. The attention mechanism still shares information across paths.
So the parallelization isn't total isolation. It's parallel computation of interdependencies, which is subtle but important. The words are processed at the same time, but they still talk to each other.
So we have words processed in parallel, with attention allowing them to talk to each other. But if the order doesn't matter for the parallel computation, how does the transformer know the sequence order? It was too tired, and too tired it was mean different things.
That's a crucial point. Self-attention itself is permutation invariant. It doesn't inherently care about word order. To reintroduce order, the transformer injects positional encodings into the input embeddings. This means that while the word in each position flows through its own path, that path is also informed by a unique signal indicating its original position in the sequence.
Exactly. Now that we have the high-level intuition, let's dive into the core mechanism, how self-attention actually calculates these interdependencies using vectors.
Okay, the how behind the what. Let's get into the details.
The first step in self-attention is to create 3 vectors from each of the encoder's input vectors, a query, a key, and a value vector for every word. These aren't just arbitrary labels. They serve distinct functions in the attention mechanism.
Query, key, value. This sounds a bit like database lookup, where you query with a key to get a value. Is that a good analogy here, asking for relevant information from the sequence?
It's a very good analogy, as long as we remember it's learned. These vectors are created by multiplying the embedding by 3 matrices that we trained during the training process.
So the model learns how to generate these Q, K, V vectors. They're not predefined, but emergent from the data. The Q asks, the K is what you match against, and the V is the content.
Next, we calculate a score. For each word, say thinking, we compare its query vector against the key vector of every other word in the input sequence, including itself.
Okay, so the thinking query vector asks, how relevant are all the other words to me? And each key vector replies with its unique identity.
The score is calculated by taking the dot product of Q1 and K1 for the word thinking's own score, then Q1 and K2 for the next word, and so on.
Dot product measures similarity, right? So a higher dot product means the query word finds that keyword more relevant. It's a numerical measure of how much focus to place on each word.
After the dot product, we divide the scores by 8, a crucial scaling factor, specifically the square root of the dimension of the key vectors, dk, which helps stabilize gradients. Then pass the result through a softmax operation. Softmax normalizes these scores, turning them into probabilities that sum to 1.
So these normalized scores now tell us what percentage of attention each word gets, relative to the word we're currently encoding. It's like a learned probability distribution over other words, in that the values are positive and sum to 1, representing weights. However, unlike a true probability distribution over discrete events, these are continuous values weighting continuous vectors.
The penultimate step is to multiply each value vector by the softmax score. This step weights the content of each word, its value vector, by its calculated relevance.
This is where the V comes in. We found out how important each word is, and now we're taking what each important word means. It's like a learned interpolation of the value vectors, where the attention scores are the interpolation coefficients. It's exact in that it's a weighted sum, but interpolation might imply smoothness or a specific curve fitting that isn't strictly present. It's more simply a weighted average.
Finally, we sum up the weighted value vectors. This produces a single context-aware output vector for the original word, blending information from all relevant words. So the output vector for it isn't just it's it mixed with some animal and a little bit of tired, dynamically decided by those attention scores. This is the new representation. Exactly. This context-rich vector is then passed through a feed-forward network. This entire self-attention mechanism is what enables the parallelization and powerful contextual understanding.
That makes so much more sense now. So how did this fundamental mechanism transform the landscape of language understanding beyond just translation?
The transformer's ability to create powerful contextual representations unlocked new possibilities. One of the most impactful applications was BERT, short for bidirectional encoder representations from transformers.
BERT. I've heard that name everywhere. So it builds directly on the transformer architecture we just explored. The ability to process everything in parallel sounds amazing. Are there any downsides to this global attention mechanism?
There certainly are. While self-attention is powerful because it allows dependencies between these paths in the self-attention layer for every pair of words, this comes at a computational cost. If you have a sequence of length n, each word needs to attend to n other words. This makes the computational complexity quadratic, or O(n) squared, with respect to the sequence length. Processing very long sequences becomes prohibitively expensive or even impossible without modifications.
So for an essay or a book, the original transformer might struggle. This sounds like a significant practical limit for real-world applications dealing with extended text, even for models like BERT.
Precisely. BERT demonstrated the true power of this new architecture, proving that the transformer generalizes well to other tasks beyond machine translation. By pre-training a large transformer encoder on vast amounts of text, it learned robust bidirectional language representations that could then be fine-tuned for a wide array of NLP tasks with minimal additional data.
So BERT essentially took the powerful context understanding mechanism of the transformer and applied it broadly, turning it into a universal language brain that could be adopted. This makes it a foundational model for things like sentiment analysis, question answering, and text summarization.
That's exactly right. BERT and models like it solidified the transformer's position as the dominant architecture in NLP. From the initial bold claim that attention was all you need to understanding its intricate mechanism and finally seeing its widespread impact, the transformer truly revolutionized how we approach language understanding.
It's incredible to see how a single architectural shift driven by the need for parallelization could lead to such a cascade of innovations. From translation to conversational AI, the transformer is truly at the core of so much we interact with today.